more probable in some metals than in others. Therefore, different metals offer different degrees of resistance to the flow of electrons. For example, copper has low resistance. It permits the electrons to flow freely with few collisions and is therefore a good conductor. Iron offers more resistance than copper. Collisions with the atoms are more frequent. In some substances, no electrons are free to move around as in the metal. All of the electrons stay with their atoms so that no current can flow. These substances are the insulators: glass, porcelain, rubber, and many others. The collisions that the electrons have with the atoms set the atoms into more violent vibration. This makes the metal hotter. If there are enough of these collisions, the metal will radiate heat and light. Heat and light from electrical sources, then, can be obtained as the result of resistance in some metals. The unit of resistance is the ohm. Its value is best understood when its relation to the other factors is explained. A pressure of 1 volt produces a current of 1 ampere through a resistance of 1 ohm. Whatever the source or the magnitude of electric energy, these factors always have the same relation to each other. So, in order to supply our great demands for electric power, we must have facilities for generating great currents at sufficient pressures to overcome the resistance of the lines, as well as to do the work. Power for industry, transportation, and light, as well as for many other conveniences we use in our daily lives. Our own sources of current able to perform these amounts of work are the electromagnetic generators. In order to explain the manner in which electricity is produced by electromagnetic generators and used in most electrical machinery, let's have a look at magnets and magnetic fields. The Earth itself is a magnet. So are the tiny electrons. All of the electrons in any object are tiny magnets. When a predominant number of these tiny magnets point in one direction, we have an extremely small magnetized block called a magnetic domain. Magnetic material, that is, material capable of being magnetized, is made up of such domains, pointing in all directions. When these domains all point in the same direction, we have a magnet. In some materials, such as copper, the tiny magnets of the electrons never line up. These materials are non-magnetic, cannot be magnetized. Every magnet has a magnetic field. Magnets may be made in various shapes to provide convenient and strong fields. To understand how a magnetic field is useful in the generation or application of electricity, let's go back to the electron, Mr. Electron, and watch him move across the magnetic field. Will you do it again, Bud? Now notice, as he enters the magnetic field, he's deflected from his original course. His deflection depends upon his velocity. Now, as we have previously shown, conductors have many free electrons. And if a conductor is moved across a magnetic field, the mechanical action causes the electrons in the wire to be deflected. just as we saw Mr. Electron deflected. This, in effect, establishes a negative and a positive charge at the ends of the conductor. We now have two charged terminals capable of producing a continuous flow of electric current just as we had in the cell. This is accomplished in practice by providing a means of continuing the movement of a conductor within a magnetic field. In all electromagnetic generators, regardless of size, the same principle is used to generate electricity. The deflection of electrons in a conductor moving across a magnetic field. The same magnetic fields and forces are also used in making an electric current perform useful mechanical work. Remember that an electron moving across a magnetic field is deflected. If the electron were moving in a wire, as when electric current flows, the deflection of the electron would cause it to push against the wire, tending to move the wire. Billions upon billions of these tiny pushes combine to provide the force. The stronger the current, or the greater number of electrons, the greater the force moving the wire. These forces on current-carrying wires in magnetic fields furnish the power for all electric motors, from the simplest to the most complex, from the smallest to the largest electric motors. The principle is the same. The deflection of electrons flowing in current-carrying wires by magnetic fields. In fact, interaction between the magnetic fields and the electrons is the basis of all electric devices. And now we may summarize that the billions and billions of atoms of which the universe is built are composed of positive and negative electric charges. That these charges are normally balanced in matter. That by unbalancing these charges, electric energy is made available. That the urge of nature to restore this balance creates electric pressure. And that the response to this urge, the action of the restoration of the balance, is a flow of electric current. The flow of electric current, then, is simply movement of electrons away from objects that have acquired a negative charge to objects whose charge is relatively positive. It's this principle that has made possible the countless electric devices which contribute to the comfort and fulfillment of richer and happier living today. Devices which will expand that to unlimited horizons in the future. Devices whose operation is dependent upon nature's design for matter, demanding that matter itself shall always seek a state of new electrical balance.